Okay, welcome to another riveting installment of Motion Genesis. So we're going to call, the first thing I'm going to do is define a Newtonian reference frame n. And again, just to clarify that nothing is case sensitive and you can have multiple Newtonian reference frames, I'm also going to declare a Newtonian reference frame using capitals, m. So I have n and m as Newtonian reference frames. Those are both non-accelerating reference frames. So they have origin points NO and MO, NX, NY, and Z, and MX, MY, and NZ. Okay, I'm going to define two more. I'm cutting and pasting so you don't have to watch me type. I'm going to declare two more rigid reference frames, A and B. So that's going to give me AO and BO and AX, AY, AZ, and BX, BY, BZ. Then I'm going to declare a whole bunch of constants here in one line. So I'm going to declare constants H1, H2, H3, G1 through 3, so G1, G2, G3, X1 through 3, EA, EB, EC, and VEC 1 through 5. So a whole bunch of constants. All right, line 5, I'm going to go in, I'm going to just declare a new vector. So here, again, this is a declaration. So H equals H2, which is a constant I had before. Of course, BY was declared when I did the referencing B, minus H3BZ. Okay, let's do one more vector here, just to show. Oh, and of course, when I enter line 5, it responds back and doing its declaration, which requires Motion Genesis to do some math. So it spits back its response, and so it's not surprising. So I'm going to do vector G, and this is again not case sensitive, it's lowercase. And of course, as we talked about before, since I initially declared A as capital, it's going to convert this G, this A into capital X's, and the G1 again is also so it's going to change cases on me as we talked about before. And like we expected, line 8, G1AX plus G2AY. Now I can do a little bit of simple math, right? So now I can say the sum of G and H. Again, left-hand side of this equation is just my choice. It's the name I made up, so G plus H. And it does the math just like expected in a mixed basis. So now let's talk about a rotation matrix. So what I'm going to do is I'm going to declare this rotation matrix. I'm going to have this rotation matrix RBA, and we declare it as 1, minus 1, 0, 0, 1, 0. So it's a rows by column format when we do this rotation matrix. I'm going to go ahead and put it in here. And so you see it's a rows column matrix. So the first row is 1, minus 1, 0. Second row is 0, 0, 1. Third row is minus 1, 0, 0. It's just like MATLAB. Okay, so that's my rotation matrix I'm going to use. So I'm going to declare that, and it's going to spit that back to me because that's a declaration. And it says that it doesn't do any math, but it's a declaration, so it's going to say, okay, I agree, this is what it is. All right, now it knows how the reference frames, or the bases, A and B related. So now I can start doing things like dotting and crossing across multiple reference frames. So let's do another vector here. This one's just AX, AY, AZ. Again, that's a declaration, so it spits it back to me. Now what I can do is I can do this. Here's a new command. I'm going to say express this vector. I named the vector because I'm super creative. And so I express this vector in the B basis. I originally gave it to it AX, AY, AZ, and it spit it back to me. It says, yes, it's AX, AY, AZ. Now I'm going to say, hey, tell me what it is in the B basis. Now that I've told you how A and B related. Now this rotation matrix, of course, is pretty straightforward. So I can see that AX equals minus BY, AY equals BZ. And so you could figure this out. It's not too hard to do this offline, but it's going to go ahead and do the conversion for me. I'm just trying to avoid a bunch of sines and cosines in this example. And so my vector is being redefined as minus x3bx minus x1by plus x2bz. And that's what it is now. So if I went and asked for what this vector is, it's gonna give it to me in this B basis now. I've redefined it basically. Okay, it didn't give it back. It doesn't give it to me in the A basis anymore. I said I redefined it, and now it's in the B basis. Okay. All right. So we did constants earlier. Now we're going to do variables. So when I do this command variable, and this is Q1, this little quote mark is the symbol for prime. So Q1 dot. Or Q1 prime. So it's going to define two things. It's going to define Q1 prime, obviously, or Q1 dot, and it's going to give me also Q1. So it does two variables, Q1 and Q1 dot at the same time. Okay. It doesn't do anything. Just like the constants, it doesn't return anything, even though I'm just declaring this in the workspace. Okay, so now I can go ahead and do things like a new command here, A rotate Z NQ1. So A rotate Z, say I'm going to rotate about the Z-axis. I'm going to rotate A about the Z-axis relative to what? Relative to N and amount Q1. Okay, so that's a simple rotation, for example. So this is going to rotate A relative to the n basis. Of course, in this picture here, NZ and AZ are both pointing out of the page. And so this rotate command says that the rotate Z command says that the Z axis is the thing that's in common between these two bases, this A and N. We'll have AZ and NZ are the same. You can have rotate X, which will mean the X axis will be constant, will be the same. Rotate Y, and the Y axis will be common. So there's one, this is a simple rotation, there'll be one axis that's common. And so in this case, AZ and NZ are the same, and the amount is Q1. So AX, AY, so this is a rotation of AX relative to NX, amount Q1 with a positive AZ sense. Right? That's the notation that's usually used in the book. So again, one more time, AX is rotating relative to NX, amount Q1 with a positive AZ sense. Okay, so that's the picture there, and it's going to spit back the rotation matrix for me. So it says omega ANN equals cosine Q1 sine Q1. Again, this is the first row, second row, third row. Of course, the 1 is here because AZ and NZ are the same. And it also gives me the angular velocity of ANN. It says, hey, you know, if you have this simple rotation going on and Q1 is a variable because you told me it's a variable, I can figure out what the angular velocity is. Wow, that's kind of cool, right? So it's telling me that the angular velocity, and the way you read this is omega A in N is equal to Q1 dot times AZ, or NZ, same thing. Pretty cool, huh? Okay, let's move on. So V, this is another vector. I call it EA BX plus EB BY plus EC BZ. So it's gonna, that's my declaration. It's going to respond back to me what it thinks it is in the B basis. Now I can go ahead and I can express that in the N basis, because again, I've told it how A and B are related, and it now knows how A and N are related. I've never explicitly told it how B and N are related, but it's got two rotation matrices, and it's smart enough to know if I multiply these things together, I can get the rotation matrix between B and N. Right? So it does that math for me. Even though I haven't explicitly told it, it can do this math. It knows A to N, and it knows A to B, so it can figure out B to N. Right? So there it goes. And it's going to give us a bunch of cosines and sines. Again, you can verify this offline. It's not too hard to do. And it gives me V, and it's being redefined. So now if I ever ask for V again, it's going to be in this long format, which is the N basis. Okay, let's do two more vectors real quick here. So I can do vec A and vec B. So vec A is in the A basis, and vec B is in mixed basis. And now I'm going to do a simple dot product between these two things. And it can do this dot product in the mixed bases because it knows how A and N are related through this rotate command, which as a result gave me the rotation matrix. So we can go ahead and do this dot product for us. And again, you can verify these things offline. Okay, let's do some derivatives. So let's define a variable. Actually, we're going to define two variables. In this case, x and x prime. Okay, that's just scalar variables, x and x prime. And I'm going to define a function here. Function equals 2x squared minus 4 plus 4x minus 5. So this is a quadratic equation. 2x squared plus 4x minus 5. And I'm going to ask for the partial derivative. So again, this left-hand side is just the things I make up. So f partial is just my made-up variable here. So a d, meaning partial derivative of the function with respect to x. So this is a partial derivative because x is a variable in time. I've already just explained that. Or declared that x is a function of time. So here I'm just doing the partial derivative of this function with respect to x, and so it gives us the result as expected. So 4 plus 4x. I can also ask for the total derivative. So d is the partial derivative. So dt is the total derivative of that function with respect to time. And so now I'm going to have these x dots in the answer. I expect to have x dots in the answer. And indeed is 4 times 1 plus x times x dot. Okay, so that's partial derivative and total derivatives of vector function of scalar functions. Okay, so let's define two more constants here, L and H. We'll do yet another vector. I had vec A, vec B, now I have vec C. So I got L times AX minus H times BZ. And I'm going to express this vector C in the B basis. It's currently an A, it's currently a mixed basis. I'm going to express it in the B basis only because I want to be able to see when I do this some of the derivatives what it looks like here. Now I'm going to take a vector derivative. This was a scalar derivative, right? So I was doing a partial derivative and total derivative of scalar function. Now I'm going to do a vector function. So I'm going to say vec dot b is going to be the derivative, time derivative of this vector in the B basis. So don't forget when we do derivatives of vectors, we have to declare what basis we're doing it in. So this is the total derivative of vec c, which is this thing here, in the B basis. Now I express it in the B basis just so we can see. If L is a constant and H is a constant, I wonder what the answer is going to be. Let's go ahead and express this thing in n basis now, just so we can see it. Of course, this one now has some sines and cosines in there because n and b are rotated relative to each other. Now when I do this derivative in the n basis, so the total derivative of vec c in the n basis, even though this derivative is 0, of course we're doing it in a different reference frame, so we don't expect it to be 0. In fact, we can see here, this is the n basis. Nx, of course, is constant, and ny, of course, is constant. So it's going to be the derivative of all this stuff times nx plus the derivative of all this stuff times ny. That's what we expect. And indeed, that's what we get. And just to show that we can also still do partial derivatives, I'm going to do the partial derivative of vec c respect to q1 in n. So again, even though it's a partial derivative, I still have to show what reference frame I'm doing the derivative in. And so I'm going to do the partial derivative of this function in the n basis, but the partial derivative with respect to q1. So I don't expect to have any q1 dots in this answer. Okay, and then of course I can go ahead and finally save this thing as my HTML file, which I can go ahead and open if I want. And so I've done this, I've saved it once before, so it's asked me, do I want to overwrite it? Say yes. So it contains all the commands, all 50 lines. Of course, this last save command won't be saved in there, but it'll be 50 lines long, my HTML file. So again, that's an example of some rotation matrices and some derivatives, basically.